Thanks, Jack. And thanks everyone for coming tonight. As Jack said, I'm David, and I'm the tech lead of the job search team here at Indeed. I've been with Indeed nearly 4 years, and over that time, have had the opportunity to work on a couple of different products. As Jack mentioned, employer, resume, and now job search. And while each team worked on something different, they were all geared towards the same thing, helping people get jobs. At Indeed, it's our job to help people get jobs, and we do that now through a variety of different ways. Most people are familiar with our job search product. Job seekers coming to Indeed can search millions of jobs in more than 50 countries and 26 different languages. However, job seekers searching for jobs isn't the only way to match up job seekers with the right position. We wanted to expand our product offerings so we could help more people get jobs. And among the ways that we wanted to do that was by flipping this equation around and having employers doing the searching for job seekers. And we did that with the launch of Indeed Resume just over 2 years ago. Indeed Resume allows job seekers to upload their existing resume or to create a new one, which then employers are able to search through using Indeed Resume Search. Tonight, we're going to be focusing on the Indeed Resume Search application, discussing how we built the product and the reasons behind the decisions that drove it. When building Resume Search, we had a great advantage. Job search is a highly successful product, and we had learned a lot from it over the past 6 years. And that gave us a bit of a head start when we started building Resume Search. There were a lot of things that we did very well with job search, along with some areas that we wanted to improve upon. And those things helped us drive the goals that we set as we started building the Resume Search application. In the same time frame, the web has evolved. There are features and tools that didn't exist when we were building job search. And so as we set out to build Resume Search using the same core principles that we apply to every product at Indeed. We wanted Resume Search to be simple. We wanted to make sure that it was simple for employers to find and contact job seekers. We wanted the product to be fast. We wanted to deliver the results to the employer extremely fast. We wanted Resume Search to be comprehensive. We didn't just want resumes in a single industry. We wanted to make sure that we had all the resumes in the same way that we want all the jobs. And relevant. We wanted all our search results to be relevant, making sure that the employers were finding the right job seekers. And tonight, we're going to primarily focus on the first two, being very simple and fast. From these principles and lessons learned since job search, we set a couple of goals for Indeed Resume Search. We wanted to build a very responsive user interface, getting results to the employer as fast as possible. Job search is very fast, but we wanted to be faster. And to accomplish this, we wanted to push more of the application into the client and to build an instant search. And for those not familiar with instant search, the way it works is when a user starts to type their search query, we request completions of that partial query. We use the best completion to perform a search while the user is still typing, giving us a bit of a head start in showing results to the user. And by starting that search before the user finishes the query, we're able to render those results faster than if we waited for the user to finish typing it and go through a full page reload. And by doing that, we reduce the time the employer has to wait to get results. And sometimes we're even able to do this before the user finishes typing. Now, this whole process is done on the client using JavaScript, which is going to help drive our next goal. We wanted to build an application that was very maintainable. We wanted to manage our client-side code in the same way that we would manage our server-side code with very good software engineering principles. In the past, we have treated our JavaScript as a way to add interactivity to our pages. But to build a better client-side application, we needed to adopt better practices. We wanted things such as good software structure. We wanted to use reusable components. We wanted the components we built with Resume Search to be applicable in other areas at Indeed. We wanted to ensure that we separated separated our presentation from our logic. In the past, we've kind of just mixed our HTML in with the rest of our JavaScript, and that leads us to very unmaintainable code, and that we were striving to build something better. And then finally, we wanted to be fast. And fast, as a goal, serves two different purposes. We wanted our application to be fast, creating a better user experience by making the interactions with the application very responsive. But we also wanted our development speed to be fast. We wanted to ensure that we could build new features quickly, easily, and safely. And so these three goals are going to be what drive the decisions we make as we build the resume search application. With job search, we used a single JavaScript file without any library support. And at that time, and for that product, that was a reasonable solution. But with resume search, we wanted to take advantage of a proven library with a large set of well-tested utilities to make our development faster, letting us focus on our application sooner. We had used the Google Closure tools as part of the job seeker side of resume, and we continued to use these as we built the resume search application. For a little bit of background, Google released the open source version of their JavaScript toolkit, which became the Google Closure tools in 2010. The pieces of the Google Closure tools are the library, the Closure templates, and the Closure compiler. And we'll start by taking a look at what the library has to offer. Across Indeed, we've been able to take advantage of a lot of the utilities that the Closure library provides, saving us time that would otherwise be spent reinventing the wheel. We've taken advantage of things such as the events library, which allows us to work with events better in multiple browsers, along with libraries such as the positioning library, again, making cross-browser development much easier. And as we continue to expand on these products, we'll have the backing of even more libraries for us to work with. And one of the great things about how the Closure library is organized is that it's very modular and independent. When building our application, we only need to bring in the specific pieces of it that we're actually going to use. So in the case of our application here, we can bring in the DOM utilities, we can bring in the cross-browser event helpers, and we can bring in some style utilities. However, we do run into a small problem. Being modular, the modules themselves have dependencies. Events depends on object and array. Style depends on object, array, and string. And the DOM utility depends on object, array, and string as well. And so we have to take some care when we're putting our application together, making sure that each dependency in this graph is met. And the order ends up looking something like this. But we can quickly see how this would be unreasonable for anyone trying to do this by hand, even for small applications. And we immediately see the need for an automated way of managing dependencies. And Google saw this as well when they built the Closure library and provided it with a set of scripts that will manage this process of building the dependency tree for you. By using the library's provide and require functions, the Closure library will determine all of the dependencies, making this problem of managing dependencies between modules disappear. And these tools are going to continue to help us as we break up our own application into smaller and reusable pieces. Another benefit of the Closure library is it comes with a very robust unit testing framework. And using the Closure library's testing utilities, we've been able to write better tests for our JavaScript. And then using the test runners, we've actually been able to integrate our client-side unit tests into our continuous integration environment. The next piece of the Closure tools is the Closure templates. As part of making a more manageable application, we didn't want to continue mixing all of our HTML with the rest of our JavaScript. This might look familiar to a lot of you. And so to do that, we want to leverage a template library, a way to make our HTML much cleaner and build it using a language more designed for building a template. The third main component of the Closure tools is the Closure compiler. And this is the component that really ties together the whole tool set. The Closure compiler is going to take all of your application code, all of your library code, and then all of your template code and output an optimized JavaScript file. And the Clojure compiler has a couple of different optimization levels. It has a whitespace only level that will just remove all whitespace from your JavaScript. It then has a simple optimizations level, which will do some safe variable renaming within certain scopes. As an example of that, let's run this small snippet through the compiler with simple optimizations. What we'll find is that the compiler is going to be able to rename the function parameter because it's safe and contained all within the function scope. The third optimization level is the one that I want to focus on tonight. Advanced optimizations is where the Clojure compiler transforms from being just a minifier or a compressor into a compiler. Again, the Clojure compiler works by taking in your whole application, all of your templates and all of your library. And when it does this, with advanced optimizations, it's able to parse it into an abstract syntax tree, allowing it to perform some static analysis and optimizations. One of the features it provides is type checking for your JavaScript. The compiler will analyze your JavaScript code, and along with hints that you can provide via documentation strings, will spit out warnings and errors when it encounters a problem. Some examples of that are if you try to pass a node to a function that's expecting a string, it'll let you know. Or if you're calling a function with too many parameters. Or if you're trying to call a function that doesn't even exist. It gives you all of this at build time, and so you don't have to wait until runtime to see these problems with your JavaScript. Another huge benefit of the Clojure compiler is its ability to remove unused code. Our initial hesitation towards using a library was the increased bloat that was going to be added by bringing in a lot of library code that we would end up not using. And the Clojure compiler helps alleviate that problem. Because it knows about every part of your application, it determines which functions that you're actually using. Typically, you're not going to use every piece of every file. And so the compiler is going to realize this, and it's only going to include the functions that you actually use in the final file that you deliver to production, giving you huge savings in your final file size. Another feature of the Clojure compiler is its ability to do aggressive renaming. And so we saw with the simple optimizations that the compiler was renaming parameters that were within a certain scope. Well, with the advanced optimizations, the compiler is going to rename everything, including all function calls. And so running the same snippet through the Clojure compiler is going to result in code that looks something a little closer to this. And this is partially a lie. The Clojure compiler actually does a little bit more with this small snippet. Having access to all of your code, it's actually going to realize that this function was only used once. And so instead of leaving the function definition in there, it's actually going to end up inlining all of your code, resulting in that initial snippet turning into just these 3 lines, of course with the white space removed. So now that we have a bit of background in the Clojure tools, let's build resume search. We're going to start by taking a closer look and see how we can break up our application into smaller modules. And so let's look at what is going to be involved in building resume search. The first piece an employer interacts with is the what and where boxes present on the home page. As an employer begins to enter a query, we'll make an AJAX request to the server, and the server then will return suggestions for that query. We'll then display those suggestions to the user, and at the same time, use the best suggestion that is returned to execute a search. Again, making an AJAX call back to the server to request the search results as JSON. When we get the response back with the results, we'll then draw them on the page. And we're going to end up redrawing a significant portion of the page on every single request to write out both search results and the refinements on the left-hand side. As an employer hovers over each search result, we'll show a preview, giving them some more information about the job seeker before they click through to contact them. Looking at this page, we start to see a couple of features that we might want to reuse in other applications. The first one that comes to mind is autocomplete. Autocomplete has a lot of applications besides just being here in the resume search application. And actually within resume search, we're going to need to have 2 autocompletes, one for the what text input and another for the where text input. Another feature that we see is the piece that is going to be taking in a query and fetching results and then rendering those to the page. And while that might not be as reusable as, say, autocomplete, it might come in handy in, say, job search. And then the third component is the preview component. Again, much like the search component, might not be quite as widely used as autocomplete, but still has applications outside of resume search. And so we're going to want to build this in such a way that preview isn't tied to the resume search application. And so these are the three features that we're pretty sure we're going to want to use in other projects. And so when we build them, we're going to want to make sure that we don't build them in a very tightly coupled way. We don't want the autocompletes to be dependent on search. We don't want the autocompletes to know that searches exist within this application. We don't, same thing with preview. We don't want preview interacting with the autocompletes or the search module. And in order to keep them very independent, the approach we're going to take is to use events. An event-driven architecture is going to give us the ability to have the modules be very independent and reusable. To get a better look at this, we're going to focus in on autocomplete and look at how that module is built. Like the resume search app, autocomplete can also be sliced into smaller components. We'll need a component for managing the text that the user is typing into the text box. That'll be our text handler. We'll also want to break the AJAX calls into a component, calling that the RPC handler. And third, we'll create a component for rendering the suggestions and listening for click events on them. And this component is going to be called the dropdown component. And so we now have an autocomplete module that is composed of three components: the text handler, the dropdown handler, and the RPC handler. And an important detail here is that the components themselves do not have any connections between each other. While the text handler does have information that the RPC handler is going to need, it won't directly call any functions on it. Instead, when a user types some text into the text input, the text handler will listen for those events and then dispatch an event, a new text event, up for autocomplete. The blue arrows are going to represent dispatching of events. And so autocomplete can then be listening for that. And autocomplete will have the logic to know what has to happen when new text is typed. And in this case, it's going to call a function noted by the green arrows on the RPC handler, letting the RPC handler know that it needs to go and fetch suggestions from the server. When the RPC handler gets those suggestions back, it's going to fire an event with those new suggestions. And again, the autocompleter is going to handle that event, deciding what it needs to do. In this case, it's going to tell the dropdown handler that it needs to render these new suggestions. And so then as a user clicks on one of those suggestions, the dropdown handler can fire that event, letting autocomplete know. We can then notify the people it needs, the components it needs to, starting with the text handler. The text handler needs to replace its text with what was just clicked upon. And this same idea is going to apply as we look at the broader application. And so as we zoom out, we see that during this whole process, autocomplete has also been firing events. When autocomplete had new suggestions, it was firing an event that the search application was able to use. And then the search application was able to dispatch that event over to, say, the search module or the preview module. And this architecture has some really nice benefits besides just making these modules more reusable. When we want to add that awesome new feature, we just have to add it to the search application. The autocomplete or the search module don't have to have any idea that this new awesome feature is on the page. And it works in the other way too. This awesome new feature doesn't have to know that it's even part of a resume search application. It's just going to be managing its own components and then firing events when it has new state that it wants to communicate with the rest of the application. And this translates well into actual code. It's not that much work to set up these listeners. In this case, we have our search application setting up listeners on the search module. On these two examples, it's looking for new results and for timeout events. And so when the search module has new results or reaches a timeout, it'll fire an event that the search application will be able to listen to and then decide what needs to be done and what other modules need to be made aware of this. Dispatching events is also pretty straightforward. In this case, we have autocomplete building up a row event, signaling that a user has clicked on a specific row. It's going to add a little bit of data to this event, such as which row was selected and some more data around that row, and then dispatch that event so that the search application can use that to pass it to the search application to start rendering more results. And the way that this app is structured, the modules are the only piece that have the components are the only pieces that have any interaction with the native browser events, the browser DOM, or the network. And this has a pretty big advantage. The modules and application are entirely free of external dependencies, which makes it not only possible, but also a lot more straightforward to unit test the functionality within these modules. The next important capability that we need to design is how to render these results for the browser. As I said earlier, for resume search, we need to redraw a significant portion of the page on every single search request. Among the things that we wanted to improve from the way that job search managed HTML in JavaScript was, well, pulling the HTML out of the JavaScript and into templates. But before we can decide which template language we want to use, we have another variable that we need to consider, and that's the trade-off of doing all of our rendering on the client side versus the server side. And so let's walk through an example of using client-side rendering on an initial page load. When an employer goes to our resume search application, we go through a full request and response, which sets up the page with the JavaScript of the search application. We then fetch the application and we'll initialize it. And at that point, the application can read the URL and make an AJAX request to retrieve the data that it needs to show. Now, this is unfortunately much longer than it needs to be, forcing the user to wait seconds before they actually see the results they expected. Now, we can improve upon this a bit by sending some of the data with the initial response. And in that way, we remove that AJAX request and response from the very end, letting the JavaScript, once it's loaded, render the results on the page. But it's still not as fast as it can be. What we really want is for the initial page load to be done with server-side rendering. And so that way, when the first request and response cycle is done, we can immediately show results to the employer and then load up our application. And after it's loaded, it can then continue taking over, doing all the rendering on the client, and making all the search calls back to the server. So instead of having the server or the client do the rendering, what we are really looking to do is have the server and the client do the rendering. We want to keep that very fast initial page load and then let our application take over and provide that very responsive client-side rendering. Now, one danger of this is needing to write our UI code on both the client and then again on the server. And we want to do this while avoiding duplicating our templates. Having our templates in two different places is not a good way to build a maintainable JavaScript application. And so the ideal solution to this would be just to use the same templates on both the client and then again on the server. And it turns out that's exactly what we were able to do. The Closure templates are a template engine that can be run in both JavaScript and in Java. And this gives us the best parts of both client-side rendering and server-side rendering. And the way this works is you write all your templates using the Closure template language, soy. And you're able to use that same soy template and use the tofu rendering utilities to work with it in Java. And then you're able to use the Closure template compiler in order to compile it to a JavaScript file that you can then use on the client. Same template, you can use it in both places. And so now, when an employer lands on our resume search application, we send the request through the server side of the application, fetching search results, and then we build up a model containing all the information needed to do the rendering. That model is then used by the Closure template engine to render HTML and then send that HTML to the client. And then after our application has a chance to load and initialize, all further requests will be done over AJAX and will be rendered on the client. And so the client is going to be requesting results over AJAX and expecting JSON responses. Now, not wanting to duplicate code for handling searching, we're going to send that AJAX request through the exact same pipeline into the same controller to fetch results, building the exact same model that we had used before. And then instead of rendering the Clojure templates, we'll serialize that model to JSON and send that to the browser. The client implementation of Clojure templates will then take over, passing that JSON model to the template, rendering the new search results as HTML, and then injecting it into the page. Both instances use the same controller and the same model, making changes very easy. Adding a new field to the search results is done by adding a single field to the model, and then adding a single, and then adding the HTML to a single template. And we immediately get that new field in both our client side and server side generated HTML, helping us stick very closely to our principle of don't repeat yourself. Another key part of client-side applications is delivering that application to the user's browser. For small applications, this is reasonably straightforward. We would include a script tag and that would load our application. However, we saw with resume search, we're going to break it up into a lot of smaller pieces. And so we're not just going to be sending a single file to the browser. We need to send the library code that we use. We need to send the templates that we built. And we need to send all of our applications. Now, being good engineers, we're going to want to break this down into a single file. And even going a level further than that, we're going to want to compile it. And we're going to want that compiled file to be a very small single file to make the download for the user much faster. And so let's take a look at what this means for our application size. And we're going to run the resume search application through a couple of the different options in the Clojure compiler. With the whitespace only optimization, we're able to build our resume search application and get it down to 126 kilobytes. When we run it with the simple optimizations, we reduce that about 18K, getting it down to 108 kilobytes. And then when we use the advanced optimizations, when we get to remove all of our unused code and we have the aggressive renaming, we drop it significantly. We're able to get it down to just 49K, which greatly helps reduce the amount of code that the browser is going to have to download on first request. And so with resume search, we see that we've been able to build an application in a maintainable way that allows us to reuse a lot of our components. We've been able to do it with using a client-side application, allowing us to have a very responsive user experience. And then using the Clojure templates, we've been able to keep our very fast initial page load. And so we can take a quick look at what this actually looks like when it's running searches. And so as the user types, we return both suggestions and search results to them, getting them results in under a second in almost every single case. Since the introduction of resume search, other teams at Indeed have learned from how we built our maintainable client-side based application and have been able to incorporate those results into their applications. Among the more interesting cases is job search. With resume search, it was pretty easy to say, let's build something maintainable when we didn't have any legacy code to be working with. There was over 6 years of history that went into building the JavaScript that job search used. Wanting to make job search's JavaScript more maintainable, another developer and I spent 5 days breaking it down into modules, much like what we did with the resume search application. Now, our primary goal when doing this was to make future development faster and easier, taking advantage of the Clojure tools, such as the Clojure Libraries Dependency Management System, the modules that we had created for the resume search application, and the advanced optimizations level of the compiler. And when we did this initial work, we didn't actually incorporate any of the Clojure library. We were just trying to break up the application to make future development easier. And so we started with a job search file that was around 41K. And when we did this work, we kind of expected it was going to increase the file size. By breaking it up into smaller modules, we were adding a couple of new functions, we were adding longer variable names. And so for this first pass, we didn't really worry too much about our code size. However, when we did run it through the Clojure compiler, what we found is that our hand-rolled JavaScript file that is no library, just written with raw JavaScript, we were actually able to reduce it by introducing the closure library. And this 6K was a pretty big deal for us. It seems like a small number, but with our level of traffic on job search and with the amount of how often we update our JavaScript, the 6K ends up to really matter. This 6K reduction in our file size results in us saving 546 gigabytes a month in data transfer and around 428 hours a month in job seekers waiting to download our file size. And so we now had all of the benefits of a modular application. We had the closure library. We were able to write better unit tests. And with all of that, we were able to still reduce our file size, keeping to our principles of remaining fast. And with that, I'll take questions.